In this video, I want to talk about another basic circuit element that is very common in electrical circuits, namely the inductor. So the inductance, or more accurately, self-inductance, is a consequence of a conductor linking a magnetic field. So if you look at the symbol for the inductor, it looks like a wire that is being wound around usually a magnetic core. So as you can see, the symbol is different than what we had for the resistors, which was like a jagged line. So an inductor is symbolized by letter L, and it is measured with the units of henries. So if we follow the passive sign convention, we can assume that if we have a current going from left to right, the positive side of the inductor is to the left, the negative side is to the right. So if we have this assumption for the direction of the current and also the direction of the voltage drop, we know that any relationship that shows the relationship between voltage and current need to have a positive sign. But how can we come up with that equation? So considering the passive sign convention, the terminal behavior of an inductor can be represented by this equation. The voltage across the inductor equals L, basically the size of the inductor, with unit Henry, multiplied by di over dt, or the derivative of the current that flows through the inductor over time. So in this equation, we have V, which is the voltage, we have L, which is the size of the inductor, and it's measured in henries, we have I, which is the current that goes through the inductor, and it is measured in amperes, and finally we have T, which is the unit of time, and it is measured in seconds. So up until now, what we had for all the elements that we discussed, we didn't have anything to do with the derivative, right? But with inductors, and later on, as you will see with capacitors, we will have the relationship to be not simple multiplication or division like we had for the resistors using the Ohm law, but also we have to do derivative as well. So we have to take into account the change over time. So as I said, the voltage across the terminals of an inductor is proportional to the time rate of change of the current in the inductor, or the rate of change of the current over time in the inductor. But this has some implications. So the first thing is that if the current is constant, so if there is no variations in the amount of current that goes through the inductor over time, the voltage across the inductor is zero. So basically it acts like a short circuit. So if you have a circuit that is going to be powered up by all DC or direct current voltages or currents, something that makes sure the current is constant, you can assume the inductor to be having zero voltages across it, or to be a short circuit, simply a simple wire. The other implication is with regard to the relationship. As you can see, voltage is proportional to the derivative of the current over time. So that means that we cannot have a current that changes instantly in an inductor, or cannot change its value by a finite amount in zero time. So you cannot have a current being zero one time and then instantly becomes 1 amps, because that requires to have infinite amount of voltage. If you know from calculus, is that if we have a jump in an equation like this, basically an instant jump, that means that during this time we have infinite value for the derivative. So since we are working with physical components, we cannot have infinite amount of voltage across the two terminals of the inductor. So this is something that you need to always consider, is that the change in the current cannot be instant. As we will work with first order and second order circuit later on, you will see how this can help us to solve those circuits more accurately. So now we have the equation for voltage with respect to the change of current over time. But what if we want to find the equation for the current in terms of the voltage? So to get that answer, we need to go through several steps. The first step is that we multiply both sides of the equation by the differential time dt. So the original equation was V equals L di over dt. So if I multiply both sides by dt, now on the left side we have V dt, on the right side we have L di over dt multiplied by dt. So as you can see on the right hand side, this dt and this dt would be cancelling out. So this makes the first equation to be converted to this differential equation, in which on the left side we have voltage multiplied by the differential time, and on the right side we have the size of the inductor multiplied by differential current. Now what we need to do is that we need to take integral of both sides of this equation. For the left one, we are taking the integral over time. So this left side is now here, this right one is now here. So we are taking the integral of the voltage over time. So I changed the variable to avoid confusion. But as you can see, we have this integral calculated from t0, or the starting time, until an undefined time, which we can specify to come up with a more general equation. And for the right hand side, L is constant, so we only take the integral of this di for the current changing from the current at time t0 to the current at time t. Again, this t is a general value. This t0 is a fixed value. And then I have changed the variable from I to x to avoid having these two the same. So based on this equation, on the right side, what we have is that since we don't know the value for the voltage, maybe it can be something that changes over time as well, we keep this integral intact, and for a specific voltage we can find its value. For the left hand side, we have the integral of the current from the current at time t0 to current at time t1. So this is basically taking the integral of a constant function, which would be L multiplied by it minus I t0. So now rearranging this equation would give us the equation that shows the relationship for current in terms of the voltage for the inductor. So the current of inductor at any given time equals 1 over L, the integral of the voltage from t0 to t, plus the initial current of the inductor. So this is very important. So if we don't have any initial current, this value becomes 0. But there are cases that we have initial currents. So you need to keep in mind that this part of the equation should always be there. So now based on the equations for power and for voltage and current, we can come up with the equations for power and energy of the inductor too. So we know from before that the general equation for calculating the power in any circuit element equals its voltage multiplied by its current. So we know the equation for voltage is L di over dt, and the current is current itself. So the equation for power is going to be basically Li di over dt. So as you can see, the power that the inductor consumes, or you can say the power that is related to the inductor, is also changing with the change of current over time. Based on this equation for the power, we can find the equation for energy in the inductor too. So we know that the power is the time rate of expending energy, or the rate of change of energy over time. So this is something that we have seen in previous lectures. So power equals the derivative of W, or energy, over time. And now we know that this equals Li di over dt. What we can do is that we can again multiply both sides by the differential time. So that makes this dt and this dt to be eliminated, which means that the differential energy is going to be Li multiplied by the differential current. Now if we take integrals of both sides, on the left hand side we have the amount of energy from 0 to W. On the right side we have L, which is a constant value which we can take out of the integral, and then we have the integral from 0 to I of y dy. And again, I have changed the variable to avoid the confusion. So the integral of the left side is going to be the energy itself. The integral of the right side, if you remember from calculus, that the integral of function x with respect to x is going to be x squared over 2, and that is basically what we have here. So this equation is going to be simplified to W equals 1 over 2 multiplied by L multiplied by I squared. So this is the equation that we have for the energy of an inductor at any given time. So to summarize, as for the symbol of the inductor, it is similar to having a wire being wound around a magnetic cord. Following the passive sign convention, if we have a current going from left to right, we have a positive side on the left, we have a negative side on the right. Based on this passive sign convention, the equation for the voltage across an inductor equals L, the size of the inductor measured in Henry, multiplied by di over dt, or the rate of change of the current in the inductor over time. We use this equation to come up with the equation for the current with respect to its voltage for the inductor. So the current at any given time equals 1 over L. The integral of the voltage over time, changing from time equals t0 to any given time that we want to find the current at, plus the initial current of the inductor. So again, this is very important. So there are cases that the initial current is 0, and this equation is going to be simplified to only 1 over L multiplied by the integral of the voltage. But if the initial current is not 0, then this has its own implications. So the general equation is like this. And then based on that, and given that we know P equals VI, you can write the equation for the power as Li multiplied by di over dt. And as you can see, The power also is proportional to the rate of change of the current over time. And then based on that, the equation for the energy of the inductor is W equals 1 over 2 Li squared. So in this video, we got introduced to inductance, or more accurately self-inductance. We saw the voltage and current relationships for an inductor. Also, we were able to come up with the equations for power and energy of an inductor.